Ladies and gentlemen, welcome to the sixth series of geosynthetic webinar under the theme Yeager Airport Reinforced Soil Slope Failure Lessons Learned. This event is brought to you by the International Geosynthetic Society Chapter Indonesia or INA-IGS. My name is Rifa Nur Kayungyun and it is a pleasure to act as your master ceremony in this event. Before we start, allow me to read the rundown of our event this afternoon. First, I will be reading the rules of the webinar. Second, there will be an opening remarks by the President of INA-IGS, Bapak Budianto Wijaya, PhD. After that, the event will be guided by Bapak Michael Doby as our moderator to start the presentation of our speakers, Ryan Burke and Jim Collin. The event will then continue with a Q&A session. We would like to ask you to stay with us until the end of the event because we will be doing a quiz with a total of 250,000 rupiah for 2 winners. We will also give you access to the e-certificate at the end of this webinar. Ladies and gentlemen, for your own convenience, please put attention to the following rules. You can submit your questions for the speakers through the Q&A feature located at the bottom of the screen. The questions should be in English. You can raise your question before, during, and after the presentation of the speakers. We expect you to stay with us until the end of the event to get the information you need regarding the e-certificates and also the soft copy of the presentation from the speakers. This event is also live streamed on INA-IGS YouTube channel, or you can directly go to the link ask.id/INA-IGS06YT. If you have any question, please contact Sandy at the number shown on your screen or on the chat box. Now, without further ado, I would like to invite the President of INA-IGS, Bapak Budianto Wijaya, PhD, to give his opening remarks. To Bapak Budi, the time is yours.
Good evening, ladies and gentlemen. On behalf of the Indonesian chapter of the International Geosynthetic Society or INA-IGS, I welcome you all to the 6th Geosynthetic webinar. This monthly webinar is one of our INA-IGS programs to share valuable knowledge from distinguished speakers from Indonesia and abroad to our members and of course all participants from everywhere absolutely for free. This month, I am delighted that we have invited two very insightful speakers with a presentation entitled Yeager Airport Reinforced Soil Slope Failure Lesson Learned. These two distinguished speakers are Mr. Ryan Arberg from Ryan Arberg and Associates and Dr. James G. Collin as President at ECE Geo Institute and President the Collin Group. As President of INA-IGS, I welcome both of you and thank you for your valuable knowledge and insight in this event. And I welcome you again, all participants. Thank you for your contribution to this webinar. I hope this webinar could be the best choice to get some valuable resource from geotechnical experts. I also thank all committee who set up this webinar. Please join our webinar and stay safe. Thank you.
Thank you, Bapak Budi, for your kind remarks. Ladies and gentlemen, now this webinar will be guided by our moderator, Bapak Michael Doby. Before I give the floor to Bapak Michael Doby, I would like to remind you that you can start submitting your questions from now, during, and after the presentation by using the Q&A feature. We would like to also remind you to stay with us until the end of the event to get the information you need regarding the e-certificates and also the soft copy of the presentation from the speakers. Now, please welcome our moderator, Bapak Michael Doby. To Bapak Michael Doby, the time is yours.
Thank you very much, Rifa. And my first job is to add to Pak Budi's message of welcoming everybody tonight to our webinar, the 6th webinar this year, 2021, organized by the Indonesian chapter of the IGS. I have a very pleasant task, which is to introduce the topic and our speakers tonight. Before doing that, I'd also just like to add my thanks to the organizers, the people who work hard in the background to make these webinars possible. There are, you see 3 of them on the screen right now by their names, but there are others as well. So thanks very much to all of those who help make these events work so smoothly. So I'd now like to introduce the topic and our speakers. It's first of all, interesting point to make that we've reached our 6th webinar, and it's the first time we're going to hear from speakers who are not academics. These are both practicing engineers. We'll hear about them in a minute. You've already heard their names and you've seen information about them. But I would like to provide a few of my own insights and comments about them before we start. So our 2 speakers, Ryan Berg. Well, Ryan, first of all, I'd like to say to you, welcome back to Indonesia. I'm afraid in a virtual way. Ryan has been here before, apparently to some of our delightful venues such as Raja Ampat, where I think he's been diving and seen some incredible sights. So welcome back in a virtual way. To Jim, welcome for the first time. I'm also, of course, in a virtual way. Hopefully, maybe one day you might get here for real and discover some of the delights of this country that Ryan has already enjoyed. One thing I'd just like to mention to everybody is that I do actually have something in common with our 2 speakers tonight, that we've all actually worked for the same organization for some part of our career or other. But what was interesting was that, in fact, slightly over 30 years ago, Ryan decided to set up his own specialized consultant practice in the US. And then Jim did something very similar a short while after that. So they both run their own specialized consultancies. They specialize in geotechnical engineering and obviously geosynthetics and the interaction between the two, which is something we're going to learn about tonight. And in fact, I'd have to say that's a really important part of what we learn about tonight, the importance of geotechnical engineering when we are dealing with geosynthetically reinforced or stabilized structures. Before I hand over, I think I'd like to mention a few achievements. You can read things on the slides at the moment, but something I'd like to mention, first of all, is the incredible contribution of our 2 speakers tonight to our field in general, geosynthetics. Between them, they have written and been part of the teams on several important publications. And just to mention a few of them, I hadn't actually realized until I looked into it that Ryan actually co-wrote a book, which you can find on Amazon if you wish, Geosynthetic Engineering. And he co-authored it with 2 other well-known figures. That's Bob Holtz and Barry Christopher. Jim has also published widely. I see a particularly interesting series of papers on pile-supported foundations using geosynthetics, which is a topic which I think many people want to learn more about and understand. So lots of interesting papers there. But also what's interesting is that they've collaborated and worked together on a number of other publications. I'm going to mention 2 in particular, because one you're probably all aware of and the other one maybe not quite so much. But those of you who've worked in the area of modular block walls or segmental retaining walls will be aware, I'm sure, that there is a design guide published in the US by the NCMA. It's a design manual. And in fact, Ryan and Jim, between them, have actually taken, well, they've been involved in all 3 editions of that document. It's currently in its 3rd edition, which is an incredible achievement. And I'm sure a huge amount of work to achieve that. And then I also noticed actually more recently, an FHWA publication, Ground Modification Methods, a reference manual, which is a fairly massive document, also with some other additional authors. And that was published quite recently in 2017. So I think what you can see from our speakers tonight is that we're going to hear from 2 practicing engineers who are really doing everything they can to project their professionalism and their knowledge into our industry, and so that we can all benefit from it. And that's very much what's going to happen tonight. You all know from the title, we're going to hear about the failure of a reinforced soil structure, which in some ways is a sad event to happen. But the important point is those last two words, the lessons learned. And I think I'll just finish with one last little point to make, is that there was a famous expression about the fact that smart people learn from their own mistakes, but the really wise ones learn from the mistakes of others. And that's what we have the chance to do. So I think I probably said enough. I've taken up probably more time than I should, but we're going to start the presentation, first of all, with Ryan, and then Jim will take over. So Ryan, the floor is yours. We're looking very much forward to your presentation this evening. Thanks very much.
Thank you. Just give me a second to set up here. Well, good evening. First of all, Jim and I'd like to thank the organizers and INA for the invitation to share this material with you. It's our pleasure to be able to spend some time with you. And before we get started, I'd like to acknowledge the full members of the team that Dr. Collin organized for this investigation of this failure. They're listed here, and it's a fairly large team because as you'll see, there was a lot of specialty work involved with investigating this large of a failure. The purpose of this presentation tonight is to share the lessons learned from this forensic evaluation of the largest reinforced soil slope failure in North America, and it was the largest reinforced soil slope built in North America. The analysis, the program was performed by the Collin Group. The rest of us were pulled in to work with Jim, and involved extensive field exploration and laboratory testing and detailed engineering analyses. And we broke some new ground in some of the work we did as far as 3D slope stability analysis of reinforced soil slopes. The entire process took over 2 years. The client was the owner of the airport, the West Virginia Regional Airport Authority, and their insurance companies.
Sorry, Ryan, may I just briefly interrupt? And we're only seeing your presenter view. We're not seeing the slide itself at the moment.
That better?
No, that's still a presenter view. We're seeing two small slides with your words.
Not
Yes.
any better?
Perfect. Thank you very much.
Okay, I don't know what happened there. Okay, all right, sorry about that. Thank you for the correction. So Charleston, West Virginia Charleston is the capital of West Virginia. It's a state near the East Coast. You can see here relative its position to Washington, D.C. Charleston is in the Allegheny Mountain Range, which is part of the Appalachian Range. So construction of the airport started in 1944. It involved the excavation of approximately 7 million cubic meters of fill to create a level area across 7 hilltops. This included cuts up to 40 meters in depth and fills up to 64 meters in height. So quite a varied subsurface profile here across the airport facility. So that was construction in 1944. In 2005, the Federal Aviation Administration required that runway 5 be extended for an emergency arrest system. What we see in this aerial view is the prior end of runway 5, and then the extension for the emergency arrest system. And that is being supported on a 1-to-1 reinforced slope here through this portion of it, and then a traditional unreinforced 2-to-1 slope over here. The 1-to-1 slope was used to stay within the airport property limits and to keep the fill from extending down to this church at the toe of the slope, this primary road here, Keystone Drive, and then what's off the photo here is a stream down by the toe of the slope. So the EMAS, or Engineered Mass Arresting System, we see a couple of views of it here. It's a series of geomembrane wrapped lightweight concrete material. The blocks are of varying thicknesses. The lightweight concrete is of varying densities, and it's designed to stop a runaway plane and prevent it from dropping off this 100-meter high cliff or end of the runway here into the valley below. And in the background, we see the city of Charleston. So that's the EMAS system. Does it work? Yes, it does work. After this was built in 2010, a regional airport jet with 34 passengers aboard aborted takeoff. And you can see as they plowed through these EMAS blocks, it slowed the plane down and they came to rest about 100 meters from the edge of the drop off there. So a very important structure, EMAS system and the reinforced slope that holds it up. So a little more of the background information. Here is the existing topography at the end of the runway. The elevations are in feet, so 10-foot increments here. The red lines are 3-meter increments. And what we see drawn in is the runway extension here, the EMAS system outline, and then this blue line is the proposed toe of the reinforced soil slope, again, to support this EMAS system and the runway extension. The subsurface investigation prior to design is the planned borings are shown here in this plan view. So again, the toe of our proposed reinforced soil slope, the top, and the proposed borings. So these are the proposed borings, but in the process of completing the work, neither B10, B11, B4, or B5 were actually drilled. Some of the borings showed water, found water in them. Some of the borings found clay seams and shale material. Some of them found coal seams, but none of that was really in any way analyzed by the designers. So these are the borings that were not performed. This work, the entire project from an engineering standpoint was performed by one engineering firm. They did the conceptual design, they did the subsurface investigation, they did the detailed design of the reinforced soil slope. They did all of the runway extension work, including all the electronics and everything else. They did all the construction inspection work. So everything was completed by one engineering firm. As such, there was no formal geotechnical investigation report prepared for the project. We didn't find anything really looking at the geology of the site here and how that factors into design. No documentation on that. We really didn't have any borings in the slope below the toe of the proposed reinforced soil slope. The groundwater that was found in 3 borings really warranted further investigation and or inclusion of drainage in the design of the reinforced soil slope. And again, shale was identified in several borings, ranging in consistency and strength from very soft to medium hard. And that material was not directly investigated in regards to the stability of the slope. Likewise, coal seams that were identified in the borings, the extent of those coal seams and the layering adjacent to the coal seams was not investigated in regards to effective drainage or on stability of the reinforced soil slope. In our investigation, we did find some records of ancient landslides that occurred directly beneath the toe of the runway extension that would occur up here. Some old landslides in 1983. We don't believe that that was investigated by the engineer of record and certainly not addressed. There was not a formal report on the design of the reinforced soil slope, but in looking back at their calculations and so forth, we could see that they designed for a compound stability failure plane factor safety of 1.3 and a global or external factor of safety minimum of 1.3 as well. Is that 1.3 really sufficient for this large of a structure in this geology and with this information that we have. If we go back into the literature, and here we're looking specifically at a table of safety factor values for slope stability published by Duncan and Wright. And if we think of this project, how uncertain were we of the analysis conditions? We were certainly closer to the large uncertainties versus small due to the limitations of the subsurface investigation. And if we look at the cost to repair the structure, and that we now have documented, the cost to repair the structure was very significant. So that really leads us down to a minimum safety factors, certainly greater than 1.5, approaching or even greater than 2 should have been used. Again, factors of safety by the engineer of record of 1.3 for compound and global stability were used. The material properties in the design are shown here in a fairly simple model: reinforced fill 36 degrees, retained fill 36 degrees, 40 degrees in a couple of zones, and the foundation of 40 degrees. Again, really not factoring in any of the shale found in the foundation or how that was going to be handled, or the coal seams. The original design utilized 3 grades of geogrid. There were going to be high density polyethylene geogrids ranging in an ultimate strength of 13.8 to 18 kilonewtons per meter. The reduction factors are listed here, as well as the interaction factors for these geogrids. And that takes us down to long-term design strength of 4.0 to 5.2 kilonewtons per meter. Again, that was the design layout. One of the things we found in our investigation in the engineering records was this conceptual design cross-section that was drawn up very early on in the design process. So this would be a cross-section of the proposed reinforced soil slope, and had 3 very interesting features to it. First of all, we see the toe of the slope was planned to be founded on bedrock, so it'd be pulled in from the edge of the slope enough to be able to be founded on bedrock. But again, our subsurface investigation was such that we really didn't know where that bedrock would be because we didn't have any borings down there. The next feature was that bedrock was fairly shallow going up this slope. That was recognized. They were proposing to excavate that out, and they were proposing to bench the back cut, which would be a standard feature in large fills. They also had proposed to bench the front face, which would allow for drainage down the front of the face and for maintenance and working platforms. None of these 3 features, however, were carried into final design. From final design drawings, this is a front elevation of the proposed reinforced soil slope. We have this hinge point here, and if you remember the plan view, this is where the slope wraps around the corner of the runway extension. So that's what's creating this V-notch hinge. We have 3 zones of reinforcement. The strongest material, P1, would be in this zone and at 2 different elevations or 2 different lift spacings. The medium strength geogrid in P2, and then in the shallower slopes, a P3 material will be used. And these distances are all in feet. And a cross section from the construction drawings looks like this. So it's a 70-meter high slope proposed. The length of reinforcement proposed was a constant length of 53 meters. On the construction drawings, existing ground line was shown. However, the top of rock was not shown. So it was really unclear what the intent was in the final design as far as excavating out this rock. And again, we don't see any benching occurring or shown in this drawing. The material for the fill, which was a very large quantity, was produced on site. It was just west of the construction site up near the top of the runway, and they processed materials. The finer processed material was used in the layers directly adjacent above and below the geogrid. The coarser material was used in between those finer grade materials, and that was to minimize installation damage. looking back or thinking back about that elevation view, remember that V notch that was shown in there, and the bottom of that V really wasn't constructible. You're really not going to go down, excavate into a V shape and start a fill. There really wasn't enough room for a working platform. So this is the first change that occurred during construction. The lower 3 meters of height of the reinforced slope were eliminated, and a rock fill was placed there to be able to come up and create a large enough working platform to start placing fill and geogrid. A couple of things here during construction. We're on the working bench here where the geogrid will be placed. We see behind us here a road. This is a haul road that the fill material had to come down to the working platform. So this haul road had to be maintained. And the other thing we see is water seeping from the soil. During construction, when they came to seeps, they put in granular filled trench drains that led the water, or supposed to lead the water, around to the edge of the reinforced fill and out at its toe at that location. But it's a granular drainage trench inside of a granular fill, so any water flow out is really questionable. Here's a geogrid being placed, and a couple of things we see here. First of all, this is not the polyethylene geogrid. This is a polyester geogrid, so a different geogrid was used than what was proposed in design. And the 53 meter length of reinforcement was not used in the lower portions of the reinforced slope. The contractor simply excavated to what they could easily excavate adjacent to the rock. So that shortened the geogrid lengths at the base, and they did not bench anything in the back cut here. They just excavated to rock. So we see here. And again, this haul road had to be maintained as these trucks came down and backed their loads down into the working platform down here. So in some cases that width of the haul road had to be maintained, and that prevented the geogrid from going all the way back to the rock in those locations. The slope face, again, was unbenched. It was a 1-to-1 smooth face, and they used a green geogrid, fine mesh geogrid, to wrap the face during construction to provide superficial protection and erosion protection. And we can see that here in this construction view from aerial view. This is the green faced 1-to-1 reinforced soil slope here to the right. That's the green facing we see. This is a traditional 2-to-1 unreinforced soil slope here. And for scale, there's the large off-road dump that we see here on top of the fill at this time. So the fill material came from here down to the RSS. Here is a completed full aerial photo of the structure. Again, the reinforced soil slope with the green facing on it, and the traditional 2-to-1 slope, and the E-mass constructed up on top. And another view of the E-mass system up on top, and another aerial view. The as-built reinforced soil structure, one of the things in the records were very good details on the length of reinforcements used. So again, instead of the 75 meter length reinforcements, in the bottom, the lengths were as short as 23 meters. The bottom 3 meter reinforced zone was deleted. They used a rock fill. And 2 grades of polyester geogrid were used instead of 3 grades of polyethylene. And in the tallest portion of the slope here, it was the highest strength geogrid that was used throughout, with tighter spacings down at the toe of the slope of approximately ½ meter, and then 1 meter spacing for the majority of the slope. And again, we see the previous ground line, the possible rock line here, and locations of sandstone and shale that were found in the post-failure investigation. So 2 grades of polyester geogrid were used, and they were conservatively used. Here are the ultimate strengths of the 2 materials This is the manufacturer's recommended creep reduction factor. The specified reduction factor was higher than that. That had to be utilized. Likewise, a higher installation damage factor had to be utilized by specification than the values that were documented by doing a project-specific test section. So allowable strengths of 6 to approximately 5 kilonewtons per meter used for these 2 grades of geogrid. The timeline. So the construction started in August of 2005 on the reinforced soil slope. The slope was completed in December of 2006. We had several years of very satisfactory performance. And then 2010 to 2014, some shallow slides were noted at the base of the reinforced soil slope. That was really deemed as being just some localized erosion by the engineer on record, and they took some corrective measures for that. But in July of 2013, so approximately 7.5 years after construction completed, 6.5 years after construction completed, some cracks in that EMAS system were noted, and those were pretty easily tracked and monitored. Then a couple years later, January 2015, significant settlement was noticed in the EMAS structure. That triggered a start of an exploration program. That program was still getting started when on March 12th, this 67-meter high reinforced soil slope catastrophically collapsed. And with that, I'm going to toss it over to Dr. Collin for the analysis on this failure.
Thank you, Ryan. Great job setting me up. I'd like to thank the organizers for inviting us to give this presentation. Ryan and I really enjoy it. We think it's really some important information, so we're really pleased to be here. And Mike, for that lovely introduction. I wish you would send me a copy of that so I can send it for all of my future talks. So thank you very much. So I've got to share my screen. Let's see. Just to confirm, can everybody see? Mike, can you see my screen?
Yes, can see it, Jim, and it's the correct one. Thanks very much.
Thank you. All right, so as Ryan said, the RSS was completed in 2006, December 2006. In 2010 to 14, they first saw what were characterized as these surficial sort of slides at the toe of the RSS as it transitions into the existing steep slope below. And we'll come back to this, but as Ryan said, the engineer of record believed this was just a surficial issue and addressed it as a surficial issue. The cracks in the EMAS were observed, as Ryan said, in 2013, and this brown line is the extent of the cracking, right? And kind of the bullnose of the RSS is here, and this blue line is the tail, the terminal end of the reinforcement for the reinforced slope. So you can see that the tension crack occurred at the back of the reinforcement. Kind of not unusual, but we'll see later that it's unusual in where it failed when it catastrophically collapsed. Some of the cracking that was observed in the asphalt pavement below the EMAS. So this was in 2014, and it continued. The cracks continued to open up. This is a joint between two of the EMAS blocks, and they did some taping of that and caulking to try to minimize water infiltration, but that continued to grow over the course of a year and a half. As Ryan said, in January of 2015, settlements were starting to occur, and the engineer of record was really called in to do more to understand what was happening with the reinforced slope. This is a drill rig attempting to install a boring just prior to the collapse. And you can see here this drop in the grade. So this is settlement that's already occurred in the EMAS or in the RSS, and it's approximately 0.6, 0.7 meters of settlement. This photo was taken days before the failure, and the failure actually occurred right at this location. The boring was stopped, and that rig was moved off the EMAS at that point. So when the failure did occur, there was a residence down here that actually the airport owned, and they moved the residents out of that, which was very fortunate. You can see this church here. This is Keystone Drive, which was totally blocked. To give you an idea of scale, so again, this is where the transition between the 2-to-1 slope and the RSS is, and you can see the RSS kind of extends to here. This vertical headscarp, which was very steep, it was near vertical, was approximately 30 meters, 100 feet. So no loss of life, a real miracle, I think, in that respect. This gives you a little different perspective, the day of the failure. So you can see that the toe of the RSS was approximately here. So when it failed, it came down the rest of that steep slope, crossed the road, and then kind of stopped at the church. So it already started to take the church. Subsequent movement of this very unstable mass took the church, and it blocked this creek. So there was flooding upstream. It was a real mess, disaster. This is a cross section taken by a drone, and the blue line here shows the day of the failure, kind of the position of the RSS. Right. And then within 3 days, another drone was flown, and that's the red line here. And so you can see it was still unstable. It was still creeping down slope. It was still a very tenuous situation. The surface of the failure, to me, really looked like a moonscape. So remember, the face was wrapped with this green geosynthetic for vegetation, but you can see that that's kind of gone. You can see the grids hanging out here. And this is I'm not sure whether to call it the coolest, but this is the most amazing photograph I think I'll ever see during forensics. So this is the headscarp that we see here, and we can see there's lots of moisture coming through this. We can see the layers of reinforcement, and those in this elevation view are approximately 1 meter apart. So there were 30 layers of this material in the headscarp that had failed. As Ryan said, that had a allowable strength of somewhere about 6 kilonewton per meter. I'm going to go back to metric, English, because that's what I'm familiar with, but it had a ultimate strength of over 10,000 pounds per foot. And so at failure, 300 kips of tensile capacity was ruptured in this failure. So really amazing. We look at a lot of failures, and we've never seen one where the reinforcements ruptured. So we can also see some of the fill that was placed, and you'll see some relatively large pieces here. So this is probably almost a meter in thickness and maybe 1.5 meters in length. Another large one here. So they were, during the filling process, putting some big material in between the lifts. And so at the failure, this is what we saw. Within about a week or two of the failure, we had a little, well, not necessarily little, but we had another piece of the RSS failed and caused this thing to continue to push down slope. So we knew we needed, before we did anything, had to stabilize the headscarp. So the deconstruction. So a plan was developed by another consultant we brought in on the project, Schnabel Engineering, to provide guidance on the deconstruction. You can see this blue line here is a temporary deconstruction to stabilize the headscarf, and then work down to remove some of the the failed mass. And so the blue line shows 9 months after the failure, how much material had been removed. And all of this material was moved back to that side of the site where they had gotten the material originally. So nothing was moved off site, but there was lots of trucking. And you can imagine this deconstruction here was a very fragile and delicate thing that took some time. So that's 9 months after construction. And then there's some intermediate stages in here where we did some borings to try to understand that failure surface. But it took, in the end, to get down and open Keystone Drive, it took over 1.5 years to do that. So that's just to remove the failed mass. During that deconstruction of the headscarf, we had many people named in the lawsuit, many parties to the construction and design. And so we had lots of experts to deal with. And so we developed collectively a program for the forensics, and that included nuclear density testing in the processed fill that sandwiched the geosynthetic, sand cone density in that same material, and then water testing in the large fill between the processed fill. And there were about 450 tests that were completed during that time. And you can see that the results are very uniform and very consistent. The weighted average of that was about 122 pounds per cubic foot at 9% moisture. So, so clearly the fill placement was done in a manner where the results, even with the varied size of the aggregate, fairly uniform results of that material. When we got down to that point where we're just 5 feet above the failure surface at the toe of the RSS, we stopped the removal process and then cut this trench about, it was about 200 feet long, about 70 some meters or something, and exposed the failure surface. We had, as again, all the consultants to all the parties were there. An extensive sampling program was done by each individual firm. You can see water already ponding at this interface. The failure surface was obvious. You can see it here. And actually, if we back up, when we were doing this excavation, it was so unstable adjacent to it that as we placed fill, you could see movement along that failure surface. So samples were collected by all the parties. Original ring shear testing to look at the fully softened and the residual strength of the material. Tim Stark was part of our team. He did the testing. We did it at confining pressures of 1,000 to 8,000 pounds per square foot, and got a fully softened strength of anywhere from 20 to 26 degrees, and then a residual of 14 to 20. And we checked those with Dr. Stark's correlations, and they checked very well. And this is the blue is here is the fully softened. So in our analysis, we used a shear strength as a function of the normal stress. As we did that deconstruction of the headscarf, we selected layers of reinforcement to sample. We did that every layer for a bit of the deconstruction, and then moved to every 3 meters. I took a sample, and the process by which we did that, we excavated down to within 6 inches with the standard excavation equipment, and a little piece of equipment excavated the next 3 inches of material, and the final 3 inches was done by hand to minimize any damage in exhuming the material. We took samples of that to a lab and performed tensile testing, both wide width strength testing and single rib. And our sampling and testing was a random sampling, if you will. And so we did both of these, and we felt that we did the wide width testing because that's kind of the standard, but we also did single rib, and we felt that the single rib results might be more indicative, because if we have a damaged grid and we're doing a wide width test on it, that damaged grid will fail first, and you get some zipper effect, which we don't think we really see in the field. So you can see a little bit of difference between the two. In the end, we used the single rib for our analyses at the failure stage. We did direct shear testing on the reinforced soil. We used a 12-inch direct shear unit, and really the reinforced and the retained soil were the same in essence, in that bearing zone at the toe of the slope was the same. We found a peak strength of 36 degrees and a post peak of 34. The original design was based on 36, right? And then 40 for the foundation, just FYI. And then for that soil rock interface, we used the shear normal function for that. And this is really the characterization of the cross section based on our forensics. So the purple here is our reinforced soil mass. You can see that it comes across and then goes up at the rock interface until we get to the sandstone. And then that sandstone face was much steeper. And then we have our existing fill behind that. The green is the bearing soil, the fill unreinforced at the toe of the slope. So the first part of our analysis was 2D analysis, 2D limit equilibrium analysis. And we'll talk maybe a little bit more about the limits of 2D analyses, but this was our starting point. And we had developed a scenario of cases we wanted to look at. And so I want to take a little bit of time to walk through these. So the initial design we looked at, and so we looked at the initial reinforcement length of 175 feet. We looked at the long-term strength of the geogrid, reduced as Ryan had showed us earlier. For the strength of the geogrid, we used the soil strength of 36 degrees for the reinforced, and then 40 for the foundation and the lower retained. And we assumed drainage. So that was our base initial design. And then we ran an analysis where the only thing we changed was the reinforcement lengths, and we changed those to the as-built length of the reinforcement. But assuming that rock was behind it, it was on a good foundation, all the other parameters were the same. Then we looked at the end of construction. And so the difference here between the second case and the third is now, instead of using the long-term strength of the reinforcement, we used the exhumed strength. So we used the strength after it had been damaged during installation, but we didn't reduce it for degradation or creep. And then at the end of construction, we changed our strength of the interface between the rock and the soil to our shear normal strength. And then we did a parametric study on the water. And then at failure, we changed and looked at the exhumed strength of the grid and also considered creep. So 5 scenarios. So the initial design with our check, assuming dry, we had a 2D factor of safety of 1.54. So if you remember, Ryan said, we should be based on the uncertainty and the criticality between maybe 1.5 and maybe greater than 2. The initial design with 175-foot reinforcement got to 1.5, right? And then when we revised it for the grid, shorter grid lengths, factor of safety went down about a tenth. And then at the end of construction, so since we're using a higher strength in the reinforcement, our short-term factor of safety actually goes up. And then at end of construction, we looked at 4 different conditions for water. We looked at dry, a low, medium, and high. And of course, our grids, it's a 2D analysis. We're considering the strength of the grid. It's uniaxial. We're considering the full strength in that in the loading direction. And so at the end of construction, with a fully softened strength, now our factors of safety start to get pretty critical. We're at 1.15 to 1.13. So not much difference with the hydrostatic pressure from the water. We still think that's a player in the failure though. And then at failure, so at this stage, we thought the really creep had set in. When we saw that the 3 foot or the 2.5 to 3 foot of vertical settlement, that our grids were really being strained and creep was a real issue. So once we looked at reducing the strength for creep, our 2D analysis showed a failure. And this is from our slide analysis, the failure surface. And this is the actual head scarp here. So these were fairly close. We felt pretty good about our results. It didn't go back to the end of the grid as you might have expected. It sheared through the grid. So kind of a summary from the 2D analysis. Reducing the strength, the length of the grid had a marginal effect. Not founding it on rock had a significant effect, right? The internal drainage was marginal, but we think it led to the deterioration of that soil rock interface. And then creep, we really think that creep did set in, and that's what in the end was reduced its strength and caused the catastrophic collapse. So that was a 2D analysis, and we're probably all familiar. We typically analyze our reinforced slopes as 2D sorts of structures, and when they're long linear structures like this levee, that 2D analysis really gives us a pretty good handle of what's going on. But if we look at 3D effects, and depending on the shape of the slope, 3D effects can be significant. For long linear structures, 3D gives us a higher factor of safety because of the end effects. But with that bull nose that we see with our structure, we thought that we ought to analyze the 3D effects and see how critical that is. And if that was an important part of the analysis, it wasn't done by the engineer of record. So there were many criticisms perhaps of the engineer of record, and we're not here to talk about those today, but one of the things that they did a really good job of, I think, was for every layer of reinforcement, they had a field sketch that showed the layout of the reinforcement. So we were able to recreate the reinforcement layers for each layer of reinforcement and put those in a 3D slide analysis. So we had a postgrad PhD student that worked for Dr. Stark, Enoch Chung, no, I'm not pronouncing his name correctly, who did some great work to do this. So with all the grids here overlapping and a failure that maybe looks like this sort of thing, the failure surface across many of the grids is not perpendicular to the strength of the grid. So we embarked on a testing program to look at the strength of the reinforcement as the loading direction varied from the machine direction to the cross machine direction. And so we did a series of tests, and basically when we got to about a 67-degree skew, we were getting strengths that were similar to the cross machine direction. So we did a linear interpolation there from machine direction to 67 degrees and reduce the strength for each reinforcement, depending on the angle of the failure surface to that reinforcement. So that was, I think, really some seminal work on 3D analysis of reinforcements. And we had to work with the software developer to actually get this modeling in correctly into the program. So let's just compare the 2D isotropic analysis. We did things in the 3D. We looked at isotropic, and then we looked at anisotropic. And so we can see that in the 3D, the factors of safety, as you might expect, were higher when we consider the isotropic strength. It all had the same strength. But when we get down to that, the failure condition, we're getting now very close to 1 for our 3D analysis isotropically. And that was really to compare and make sure that our 3D analysis was, providing us good information in regards to our 2D. What we really wanted to see was, kind of that anisotropic effects. And you can see that there is significant reduction in the factor of safety from an isotropic to anisotropic. And that, in fact, with our 3D analysis, we're really just about at 1. So again, we felt very good with the results. This is the failure mass in the 3D analysis. And I think the angle of this was like 2 degrees off of the angle of the actual failure mass, direction of the failure mass. So that was a good check on the analysis. We felt very good about that. So we were feeling pretty good about our analysis, but we still thought there were some issues that we needed to resolve. And one was really this time of 8 years where the system seemed to perform pretty well. And then all of a sudden we got deformations and failures. So, the limited equilibrium performed under our various loading conditions gave us that idea, but it's not capable of evaluating the stress and deformation prior to failure. So it's just at that failure condition. So we used a flat 3D slice that was a 0.5 meter wide at the bull nose at the center line of the failure to better understand the kinematics. And we did it at the end of construction. Right, so we didn't do the full-blown analysis. We really just wanted to focus on the end of construction. The GeoGrid ultimate strength was used to construct our 3D model. And then once the GeoGrid was activated, we used the exhumed strength. And the GeoGrid's model is a nonlinear cable element that when it yielded and ruptured, it didn't provide any more stability to the structure. And so I'm going to show a little video here in a second, I hope. But so here's our reinforced soil mass in our FLAC 3D model. We used this was our shear zone where we used the shear normal strength of the reinforcement. And then in the upper rock interface in the sandstone, we used the soil rock interface of 40 degrees. And I'm gonna, let's see how I can. All right. Okay. All right. So this is a video. I'm going to stop this a couple times. So I'll stop it right here. So we're looking at, you can see the GeoGrid reinforcement as the horizontal lines. They're hard to see here, but they're there. And the color of those will change depending on the load in it, all right? And then for deformation at the interface, you'll see a change in color also. And then at the bottom here, you're gonna see we're reducing the shear strength of this interface So this is on the bottom scale, that's the ratio of that reduction. So you'll see when we go to from a strength of 30 degrees, or I forget exactly what it was at the start, to our reduced strength, you'll see the deformations occur here. So let's so I'll stop it there. So we can see there was the deformation started at the toe of the slope, and then they kind of crept up here and developed across the full failure surface. You can see that the reinforcement, it ruptured here. Internally, there were locations where it ruptured. We were never able to verify those with the failed mass. So let's see. So I think I've really covered that. So we looked at kind of the shear bands that developed during that analysis. This was very interesting. So remember, the first tension crack was back at the back of the reinforcement. Yet when it failed some distance in front of that and ruptured all that reinforcement. And so there was always a question of, wow, that seems odd. I wonder what's happening. And when we did the deformation analysis, we found prior to failure shear bands that developed back at the location of the original crack. As further deformations occurred, it led to the failure. And it was really that sandstone rock that forced, I think, the failure up through the grids. So, so the failure mechanism was a compound. We really showed that with all three analysis. So it was below the RS along that shale rock interface. It occurred 8 years after service, and it was a shale claystone interface that decreased in strength from the peak to somewhere near the fully softened strength during the course of that time. The 2D and 3D limit equilibrium analysis and the 3D deformation analysis were consistent. We felt very good about that. Deformation analysis confirmed that a reduction in the strength occurred along that soil rock interface and really explained the time that it took for that failure to occur. And then the 3D limit equilibrium analysis also shows the importance and some configurations of considering the anisotropic properties of the reinforcement, something that we typically don't do. So to sum up, the reinforced soil mass was removed, and then the EMAS had to be put back in place. And the director of the airport, we had many conversations on what we should do to replace the failed RSS. And it's clearly Ryan's, in my opinion, that the reinforced slope is the ideal solution for this system when it's designed and installed correctly. When I kept trying to convince the director of the airport to do that, he finally said to me, Jim, look, if I go to the board and recommend we rebuild it with the same structure, they'll fire me. So Schnabel Engineering came in and designed the replacement at soldier beams, drilled socketed into rock with rock anchors here, and fill another set of soldier beams. Those were anchored into the rock also, some tiebacks between those, and then geofoam here. So pretty massive redesign. There are, and we've covered a lot of ground today. There are 2 papers that we've published on this, and I would, if you're interested, you'll get this in our copy of the presentation. So they go into more detail. Here they are. And with that, I'd like to thank everybody, and I'll stop sharing my screen.
Oh, yeah. Jim and Ryan, first of all, thank you again. I have listened to this talk before, and I must say it's definitely worth listening to it again. I can assure everybody. I think actually surprising. I think so many people are completely mesmerized by this. We have a few questions, and we definitely have a few questions. I'll come to them shortly, but um, just to give you a kind of observation, and I think it's so important here is the fact that we are a geosynthetic society, but it's so important that geotechnical engineering is foremost in all of our structures, but particularly something as massive as this one. And I think what we see from this presentation today is the absolute importance that that people don't forget about the geotechnical engineering side of things when they're looking at a structure like this. But I mean, if you've got any further comments on that, I'd be pleased to hear it, but maybe come back to that. But just one little thing, I'm pretty sure I would thank you very much for trying for converting to kilonewtons per meter, which I know is not your favorite unit. I think you're a factor of 10 out, but maybe we'll just look at that before you make the final PDF, because those strengths I think should be times 10 roughly. Because we had a comment about that, which I did answer to just now. So anyhow, let's have a look at some of the questions. Quite a few of them come from Pat Go. Pat Go actually has a similarity with yourselves. He also is I'd say he's a small specialist consultancy practice in the geotechnical field. So probably he feels very closely with the kind of work that you're doing. But he has a few questions. And the first one is, if granular free draining material is used for the backfill material, do we really need the drainage layer at the end of the MSE wall?
Well, it's a granular material. There was a variety of material there, but without a chimney drain and a blanket drain at the bottom, you really don't know where that water is going to go. There is going to be some layering. Any water coming through the back fractured rock is going to go out into the fill. But more importantly, as it goes down towards the foundation, the RSS, how does it get out of the system? There's no blanket drain there. And what we saw was that water would go down to coal seam layers, down to the clays, and that's where it would concentrate, and that we believe led to the softening of the foundation soils and to the collapse. So we really see drainage systems in RSS as being a fairly inexpensive safety factor, and it's something really to control the water. Where do you want it to go, or do you just want it to meander and end up where it ends up? So we felt there should have been a drain system in here. We also felt that the lateral trenches where they came up with the seeps would not have carried the water laterally to the edge of the reinforced soil slope. It might have distributed the water some, but it was still just going to fall into the reinforced fill because that was free draining. So we really just kind of distributed the water, but did not control it.
And I guess I would only add to that, for this structure, the engineer of record specified up to 50% fines in the reinforced fill. That's not what was there, but he specified a material that wouldn't drain at all, yet didn't put a drain in. So that would have been one of our criticisms of the design, in addition to Ryan's comments.
Okay, well, thanks. Yeah, I think I mean, drainage, as you quite rightly say, just such an important feature of structures of this type. Can I just ask a little supplementary question to that, because it's always slightly concerned me that for those who don't know it, actually this particular structure is features in the more recent FHWA manual for reinforced soil design. It's one of the case studies, and it mentions in that case study that there was a use of geosynthetic drainage materials. Now, was there actually any? I mean, I was amazed to hear that in such a big structure. Was there any evidence of that?
No.
No, that was one of the issues also. So the publications did speak about drainage in the structure, yet there was no drainage material. There were no bill of lading tickets for drainage material that was included. There was nothing that we found. There was no drainage composite when we deconstructed it. So it wasn't there.
Good one. Probably a relief. Okay. The second question from Pat Priya here is actually, you've actually answered this, I think, very nicely at the end, but I'll just repeat it because it's a good question. It says, regardless of this failure, by considering and anticipating all of the technical aspects, would the RSS still be recommended to apply on this site confidently? I know you've answered that, but I don't know if you anything else you'd like to say about that.
Ryan, I kind of said my piece. You got anything else you want to add to it?
Oh, no, I agree. We felt that was the best solution here if it was properly engineered and if the geology was studied and understood on the site.
Okay, so Pat Go again has got another question. This is to do with geometry. And he said another question here is, how many meters more from the toe of the reinforced soil slope to the base of the, I think he means the distance from where the reinforcement finishes until you meet the original slope beyond the toe. How far should that really be? Because it seems that they were, one was actually meeting the other in the cross sections. Says the design looks very risky by stopping the reinforced soil slope at right on the original slope line and not set back.
Right.
Right.
I mean, the original. Go ahead, Ryan.
Remember that conceptual sketch where they pulled the toe of the slope back onto competent rock? That was a good idea and something they should have followed. As it turned out, they did take it right out to the edge of the existing slope. They didn't have borings there. They don't know how much soil fill they were sitting on before they got to rock. None of that was investigated or documented.
Okay, that's good. No, thanks. More of a comment from Pat Go again. He says, it looked a progressive failure starting from the toe of the reinforcement. And I think that matches your description, surely.
Yes. Yeah. And I actually think those superficial failures that were occurring earlier on may have been an indication of this, the overall instability, occurring. We weren't able to really prove that one way or the other, but to me, when you look at the deformation analysis, it really starts right there at the toe. And so that those superficial failures that were occurring may have been the first signs of distress.
Yeah, like I think it's a good lesson. I mean, I think surely there's a lesson that whenever you see a significant mass movement in a structure like this, you have to think something's going on. But yeah, that's for me always been a strange, this whole episode, the fact that there were movements noted quite some time before the big failure happened, yet that wasn't sufficient to put in any, say, extensive instrumentation or anything like that. I mean, I don't think that happened, did it? In fact, it's one of my points. I don't think there was any instrumentation put into this massive slope at all, was there?
No, it's incredible that the 240-foot high slope, the first major slope in the U.S. of that magnitude, and no instrumentation was put in as part of the design and construction, right? We should have had instrumentation in there that was telling us, years before the failure that we're getting movement at that interface. So you're correct. That was surely an important thing that wasn't included.
Yeah. Okay, next good question here from Pablo is, would a proper drainage system, I guess, have prevented degradation of the rock soil interface by water? The softening, in other words, I guess.
Well, it's hard to say. I think the degradation was both from the water and the stresses, right? So it wasn't just water, but it was a combination of the stresses from the structure that was placed on top of it and the water.
Yeah, I think if the water's allowed to get there, it's going to get there, isn't it? To cause difficulties. Yeah.
Yeah, so we would have recommended that that the rock be fully exposed there at the base of the slope, and those clay interface areas, those coal seam areas, wherever they came out, those should have been removed and those areas replaced. That was part of chasing out the poor geology there that was not done.
Yeah, I mean, I think your observation about those earlier, or the earlier instability on that slope towards the bottom, anyhow, that seemed to be a rather important warning for the investigation of that structure, I'd have thought.
Yep.
Okay. So from Justian, it says here, how about the different stiffness between the rock and the fill materials? The failure seems to move at the surface of the rock. You've shown that, but any additional comment about that? Was that a very major part of the generation of the location of the failure?
I'd like to pull a photo up here. Wow. What happened? Yeah, I would like to pull it up. Let's see. Here we go.
Oh, we can see that pretty well.
Okay, so this is out of the G&G technical paper. So this is the excavated rock after failure. And this is the sandstone up here that we're seeing. And you can see how smooth that was. It wasn't benched at all. So that's where the failure plane, after coming through the clay interface, chased up to the sandstone and then shot up into the reinforcement, caused that failure as it came across this smooth sandstone. We did talk about going into the laboratory and doing some fill material to sandstone, direct shear testing to better define those properties. But as our analysis showed, we could match the failure with all three stability analyses methods, and where we're at with the project, the amount of money spent, we couldn't get authorization or justify an expenditure to do that. But that would have been interesting to be able to better define those properties. And while I've got this up, I'll also add, so that tieback system that Jim showed that replaced the RSS and the tieback system with the lightweight fill, that was built on top of this sandstone ledge. So it was founded on good, competent material back on this ledge.
Okay, thanks very much. Interesting. Okay, so I'll carry on going down the list with some good questions here. So this is again from Pat Go. He says, how do you normally measure or place the chimney and base drain in order not to cause a weak plane? Layout of those drains, I guess, the optimum layout to avoid creating or tending to create a plane of weakness.
Well, a chimney drain should follow a bench back cut. I mean, this was a 80-meter high fill. It should have been benched back cut. Even if it was a 2-to-1 slope, it should have been a bench back cut to prevent the stress concentrations along that smooth face of the stone. So you put in a chimney drain, that should follow the benching. And a blanket drain, yes, that requires some planning to and material selection to make sure you're not putting in a weak plane. But generally, if it's good crushed granular material, you'll have a higher shear strength along a blanket drain.
Yeah. No, thanks, Ryan. Okay, so now next question is quite a long one. I'll take it slowly because I think it's an important one. But it's from Mr. Avik, who I happen to know is listening in from India. So what would you have? What would have been the behavior of the high slope if it is designed in multi-tier slope of say 10 meter with intermediate horizontal benches and designed length of backfill reinforcement ensuring adequate safety factor in all different modes of failure, covering the rotational, translation, under different water table conditions in static and seismic condition. I think he's covered almost every possible thing, but I don't know if you're able to read that as well. But I think he's really asking more about what happens if perhaps you approach the whole design in a more thorough way, as you've already mentioned.
Yeah, I would say that if you didn't account for that rock soil interface and get rid of that, then it would still fail. If you did everything correctly, as we said, the structure would have lasted and we wouldn't have learned all these interesting things.
From Dwi Herianto, is there a failure of slope deflection on the original soil? Yeah, I'm not sure I fully understand that. Let's move on. So this is Panji Utomo. Okay, on Panji. As I understand, the toe part of the MSE wall is less than designed due to the presence of a rock layer. So I think this is a question about that rock layer that was placed in at the toe where it shouldn't have been in the original layout. Should we extend the toe of the MSE wall as part of the design or add a stronger geogrid layer with regards to that particular detail?
I think he or she's talking about the zone below the RSS that was filled with big stone, but a kind of our reinforced material, right?
Yep.
And yeah, I think we feel like we've talked about this. If you had stepped the face of the slope back, so it's sitting on rock, you would be out over the residual material there, the colluvial material that was there. And we would have extended the reinforced mass down to the interface with the rock. So we wouldn't have had a 3 meter section of unreinforced material at the toe.
Right. Yep.
And I would just add that when you look at the construction plans, again, that V notch was not a constructible feature. So there shouldn't have been a V notch. It should have been a width where a contractor could work. Likewise, that haul road was another constructability feature that wasn't fully appreciated during design. But again, constructability is always part of the design process.
Yeah, for sure. Mr. Avik from India has come back with another question. I think I'll summarize it having read through it, but he's asking if there could have been an improvement by combining some soil nailing or anchoring of the existing materials, combining that with a reinforced soil slope to bring up the fill as required. So the additional strengthening from rock anchors or soil nails, could that have helped the problem?
Well, we didn't analyze that. I mean, I maybe it could have. I don't think that was the answer to the problem. I think getting that soil, that interface out was really the issue, right? And so I wouldn't want to leave it in and then try to add more reinforcement to handle that, right? Which I think is what that question is really indicating.
I think so, yeah.
So,
yeah. You could have been strengthening up a bit that didn't really need strengthening up, I guess, and leaving the critical point still there. Actually, we have a very short question here. What causes failure? Well, I think you've kind of been through it. I mean, would you identify the single important trigger? I mean, the thing was moving a bit, but was there a single important trigger that actually made it go?
I don't think we ever really came to a conclusion there was a trigger. Most of the time there is, I think, right? Most of the time when we do a failure, I mean, there was rain in that March time zone right before the failure. There was rain. So that maybe was the trigger in the end. But our analysis kind of showed that no matter where the water table was when we did it in our analysis, it really had a marginal effect. So either we didn't capture its impact correctly, but I think we did. So we didn't come up with a traditional trigger. We came up with a list of things that contributed to it, but not any one that was the straw that broke the camel's back.
Yeah, interesting. Yeah. I think sometimes difficult to tell exactly what it is, but it's a combination of things that make it fail. What is the trigger? Difficult to say. Okay, so we have a last question on this list anyhow from Professor Wijoyo, who was our speaker at our last webinar. And he was also talking a little about some failures of retaining walls as well. And he just, a short question, says, from analysis viewpoint, are there any insights when we have to explicitly incorporate the geogrid anisotropic behavior, which you covered very nicely, I think, but any further insights about that? I mean, I guess possibly from the point of view of the initial design, because you're looking in great detail at something that you know, a huge amount of effort's gone into investigating, but with day-to-day design, maybe we don't have all that luxury. But is that something that that we should have a viewpoint on?
I'll start and then let Ryan finish it. It obviously depends on the geometry of the structure, right? And so with our structure, it was obvious, and I think Ryan was the first to say, Jim, we need to look at this 3D with this bull nose. This could have a big impact. If it was a inside radius, I'd say 3D is probably not needed, right? But so you have to look at the geometry to determine when we need that 3D analysis. And then 3D analysis isn't easy, right? I mean, so it's not a standard, but for a structure of this magnitude, right, I think it was warranted. Now, if we have a 30-foot high structure, maybe we just increase the factors of safety significantly, right, to account for the 3D effect. And there are certainly papers, Tim Stark has written several papers on what would be maybe an appropriate 2D factor of safety for a 3D sort of structure. So that might be something that you consider, right? Ryan, you got any?
I would just add that if you have to go to 3D analysis and look at the anisotropic properties of the geogrid, we found that to be quite challenging. We said, okay, we need to come up with the strength when we're going through the layers at a skew, and the team sat down and we all kind of independently drew up what we thought would be reduction values and kind of plots as we're rotating off of 90 degrees. And then we went to the laboratory, and that was very challenging to be able to do that testing and then to interpret that. But what we found was the effect was much more significant than any of us thought going into it prior to the testing. So it's a challenging area to look at, but again, only needed if you have this three-dimensional effect, which is going to be a fairly unique structure.
And I might add to that. So the software that we used, when it modeled the resistance of the reinforcement across a failure that cut across the reinforcement, let's say at a 45-degree angle, that length of the reinforcement is longer, right, than its width. And originally, the modeling considered for every foot of that length the ultimate strength of the reinforcement. So this was early on in this 3D software development, but we had to work through with that developer the way to model that the reinforcement is as it crosses the reinforcement at some angle. And so we have confidence because we checked it for the software we used. I don't know whether other 3D software that includes reinforcement has correctly modeled that. So I think that's a question if you're going to do that analysis, to make sure you understand how the reinforcement's being handled.
Yeah, I mean, I think that there are some really important lessons there. I mean, that's the whole purpose of your presentation and what we're learning tonight. But these issues on unusual geometries and you know, not thinking hard about them, I think that this is something that everyone should take home tonight, the importance of being very careful. And it's interesting you mentioned the convex and the concave slope, and you know, which one is likely to be more difficult to take into account. And of course, you must be right. And I think this proves the point. There's the last question here from Pat Go again, but it's you mentioned clay shale. I'd have to say in Indonesia, many parts of Indonesia, there are clay shales, and these are materials that worry people significantly because of their ability to soften and create unfortunate failures and so forth. But he says here, I noticed there is a clay shale layer in one of the drawings. Any investigation on the degradation of the clay shale layer after the failure?
Not the only investigation was to take that failure surface and look at the fully soft, kind of look at the residual fully softened strengths. We didn't do any work to take a sample below the failure that hadn't softened yet and see its degradation mechanism. Right. I mean, it was that the structure was there for 8+ years. We took 2 years to do our analysis. We didn't have more time to look at kind of how that interface would deteriorate.
Okay, I think actually I was particularly interested to see that you'd done the ring shear testing. I might be wrong, but I'm not sure if there's a ring shear instrument at all in Indonesia. And considering we have clay shales here, it could be a good idea to understand their both their fully softened and their residual strengths better. I mean, my origins are the UK, and of course in the UK we have a lot of very high plastic clays like London clay, which have incredibly low residual strengths, and,
right.
and we're kind of familiar with it. But these clay shales do catch people out, I think, quite often, and that knowledge of that would immediately explain the kind of behavior that is seen often with structures founded on clay shales, especially if they're slightly difficult angles, and it encourages large deformations and failures to take place. So, yeah, I think very important material to think about. Now, I think we've just about come to the end of the question. There is another long one here from Mr. Avik. I don't know. I'm waiting for the organizers to tell me we're perhaps close to the end of question time, because you gentlemen have certainly been talking to us for a long time now, and a lot of incredibly valuable information. But this is to do with, right, very interesting presentation. The critical point of the entire presentation is that the interface failure between the existing rocky slope and the newly added soil slope, which needs to be taken care of with composite reinforced earth technology by connecting the soil nailing. This is about soil nailing again, but I mean, you've already mentioned that particular detail wouldn't have been fixed by soil nailing. I think that critical shear plane, if you like, that deteriorated below the structure. I mean, do you feel soil nailing it could have improved that if it had been anticipated?
No, remember we ruptured 30 layers of reinforcement that had an ultimate strength of over 10 kips per foot. So that's 300 kips of load that we're not going to put soil nails in and connect them to reinforcement to create any sort of system that's going to take that load. So to me, the clear answer is to excavate that interface and get rid of it and sit on the rock. If they had, taken 5 feet of material out and stepped it, I think the structure probably would have continued to be there.
Yeah, and I would just add again, it was incomplete subsurface investigation, poor understanding of the geology there, and to get rid of that interface of that clay interface at the bottom of the reinforced soil slope, and then the lack of benching either by design or by the contractor as they came back up through the upper portion of the shale and into the sandstone. All those really contributed to this failure plane formation and the ultimate failure.
Okay, well, I think that's a really, really important summarizing comment there, Ryan. Thanks for that. I mean, I think I've been told that, gentlemen, you can rest now. I'd like to again, thank you very much. I learned more and more this time because that really was a fantastic presentation, and the amount of information there, and I think the development of that that FLAC modeling came a bit later compared to the very you've been building it up. And perhaps just one last to make is that, and it's something I like to remind people, that generally certainly a natural soil slope, it's probably got there through a process of failure. It's probably reached its current condition through a process of failure. So it is wise to anticipate the fact that you could, in a natural slope, have some problems. Anyhow, one more time, thanks very much. I'll bring my moderator job to a finish now and hand back to Rifa to complete the rest of the session. So thanks very much again, Jim and Ryan, and Rifa, back to you.
Once again, thank you, Ryan Burke and Jim Cullen, for your excellent presentation. And thank you also to Bapak Mike Doby for guiding the session. Next, I would like to invite all of you for the chance to get the very interesting prize by joining a very short game we have prepared. To give you a disclaimer before we play, everyone can join this quiz, but for technical reasons, only those who live in Indonesia are eligible to get the prize. You can now directly go to your browser on your phone or PC and then type menti.com, MENTI.com, menti.com. You can directly go to your browser on your phone or PC and type menti.com. You have to type the code number shown on your screen or also there in the chat box. The code is 61405527. Once again, go to menti.com and put the code 61405527. Then fill in your name and make sure it is the name you submit in the registration for this webinar. So later, if you win, the committee will easily contact you for the prize. Remember, the prize is 250,000 rupiah for 2 winners, and you will not want to miss this chance. Go to menti.com, put the code 61405527 and fill in your name. We will be waiting for more attendees to join. Wait, let's see the quiz page. Let's see how many have joined us. You can go to menti.com and use the code 61405527. Okay, we already have a lot of people joining. We're still waiting for another minute. We have 61 people joining us for the game. There are 3 questions. The questions have been prepared by our speakers. You have 30 seconds for each question, and the accumulation point later will determine who win 250,000 rupiah for 2 winners. So the first winner will get 150,000 rupiah and the second winner will get 100,000 rupiah. So the total is 250,000 rupiah for 2 winners. Go to menti.com and use the code 61405527. We have 71 people joining. We're still waiting. We're waiting another 30 seconds. Go to menti.com and use the code 61405527. Make sure you have stable connection so you don't miss any question. We're waiting for another 15 seconds. 74 people. Come on, total of 250,000 rupiah for 2 winners. The first winner will get 150,000 rupiah and the second winner will get 100,000 rupiah. And only those who live in Indonesia are eligible for the prize, but everyone can join this fun game. Okay, I'm gonna count 5, 4, 3, 2, 1. We're going to start the game. Okay. Question 1 of 3. Answer fast to get more points. Soil reinforcement used was uniaxial geogrid. Post-failure testing was performed. The AIS tested strength considered what degradation mechanism? Is it durability? Is it installation damage? Is it creep? Or all of the above? You have roughly 15 seconds to answer the question. Is it the first, the second, the third, or is it all of the above? 5, 4, 3, 2, 1, time's up. Let's see who lead the leaderboard for the first question. So the answer is all of the above. 31 people answered right. Let's see who's leading. For the first question, we have Iman Alfikri who answered fastest and also answered the correct one. Everyone has to catch up. We have other 2 questions. Let's see. Second question. Question 2 of 3. Answer fast to get more points. Let's catch up. The failure surface of the RSS can be described as what type of failure? Is it internal? Is it global? Is it compound? Or none of the above? You have roughly 20 seconds to answer the question. The failure surface of the RSS can be described as what type of failure? Is it internal? Is it global? Is it compound? Or none of the above? 5 seconds left. 3, 2, 1. Time's up. Let's see. What is the correct answer? It's compound. 27 people answers right. So who is leading for the second question? Destri answered fastest, but still Iman Alfikri leading the leaderboard. For the third question, we're going to see the final winners, 2 final winners for all of 3 questions. Let's go. Question 3 of 3. Answer fast to get more points. The soil rock interface strength deteriorated over the 8 years the RSS was in service. What contributed to this loss of strength? Is it water? Is it high shear stresses? Or both A and B? You have 20 seconds to answer, but remember to answer fast and correct to get more points. 10 seconds remaining. Last 5 seconds. 4, 3, 2, 1. Time's up. Who's going to win? But first, the correct answer is both A and B. Let's see. So 2 winners of this quiz. Congratulations to Iman Alfikri with 2,869 points, and also Destri with 2,861 points. So congratulations to Iman Alfikri and also Destri who won this quiz. Okay. We invite you to the upcoming webinar under the theme Failure Investigation of a Geosynthetic Reinforced Soil Slope Subject to Rainfall. We'll be speaking in the upcoming webinar is Guo Xin Yang from National Taiwan University. For the upcoming webinar, the presentation will be delivered in English. You can register at the link s.id/webinar INA-IGS 07. Once again, for the upcoming webinar, you can register at the link s.id/webinar INA-IGS 07. Ladies and gentlemen, we have now reached the end of the event. Before you leave this webinar, we would like to inform you that you can access your e-certificates and the soft copy material from the speakers by visiting the link s.id/info INA-IGS 06. After filling the quick survey, you will be redirected to the e-certificates. Once again, thank you for your participation. We hope we can see you at the next event. At last, good evening and stay healthy, everyone.